Any questions? Yeah, so we have been using the estimator and sampler. Okay, this is just a quick overview. This is from the other video. Anyone actually watch their videos? There are 7. Any of you here watch the video? Okay. Yeah, so today we're going to go through some of the notebook by Dr. Wang from IBM. Just to go over this slide. So this is to run on real device. Okay. So you need to, just to emphasize, you need to initialize the Qiskit runtime. From this, you import Qiskit runtime service, estimator, sampler. Here, this estimator, who can tell me is V1 or V2? This one is V1 because it doesn't say from the runtime, you don't use V2, then it's V1. So initialize, you say service, this is runtime. Backend, you can specify which backend you want, or you find the least busy one. In the past, we have done this. Number of qubit. Okay, this is a really crazy one because it says real random emission 120 127 qubit. Okay, it's a emission for 127 qubits. This random emission is from here. Corner info. This will be a large matrix, 2 to the 107 times 2 to the 107. And you say, this is a circuit. Then you define observable, Z, basically Z times 127. So it's a bit string of Z's. You initialize, here we use estimator, so, and you say, I think this need to change to mo equal to backend. So that this is the old code. So this is mo equal to backend. Invoke estimator and get results. And yeah, so you can see that it still use circuit. Still use circuit. So this is the V1. If it's V2, right? V2 you will need to use pub. Pub is a list of tuples. Circuit. This is estimator, will be observable. Parameter. Accuracy. So you should be able to recognize whether it's V1, V2, and is any place that you need to change. Okay, session. I think we use session and also batch, right? With session. So session allow a collection of jobs to be grouped and jointly scheduled by its runtime. This is because you want to use some feedback of the previous result, and you can determine the next parameter, like in VQE, and then requires some classical computation in between. Okay. So this is use the context manager using this with statement with session backend equal to backend session that you do the estimator, right? Here is correctly used mode equal to session. Estimator, you can say option, so that is option here. People shots. Okay, so this is results. Go to minimize. This is a minimization. Minimization, you have the cost function, parameter on that. This is on that, I say Hamiltonian estimator, and using the methods called we assume something similar. Okay, let's see. Good. So this is the schematic diagram. So your estimator, the first job, and then some time to do classical processing, and you repeat, and this can be feedback to this. For batch, you don't need to have this idle time. All Java independent, so there's no classical processing needed, but it's the same way of writing. We also try this batch as batch. Okay. Okay. This is something in the estimator. You can use a resilient level, mostly estimator. You can see. So if you have options, resilient level options set to be 0, then there's nothing. If it's 1, this is default. There's some minimum mitigation. So it's associated with the readout. Estimator will use this readout method. So I think there is a lab that talk about mitigation. This is for the samplers using this. Level 2 for some medium mitigation. Like this is minimum, medium, and heavy. So this second level typically reduce bias in estimator, but it's not guaranteed to be 0 bias. Estimator is also use second level use 0 noise extrapolation. For sampler, there's nothing. It might be in the future, you know. The third level has heavy mitigation. So in order to do these, for example, real noise extrapolation, you need to run more circuit. And here you run even more. This level 3 use probabilistic error cancellation.
So they do it for you, like
they do it for you. So that's yeah. In the past, we have need to implement these mitigation on our own.
Nice.
I think we've tried this one. Well, that time IBM has some package, but you have to incorporate. You have to do it
like
on your own. Yeah. Oh yeah. So this is what I was started to show, right? He has 7 video, but you don't need to watch all of them. Just some of the later one is here. So I started the episode 3 of the world, and there's also episode 4 primitive, episode 5 dynamic circuit. Yeah, so these are 3 really good videos. I encourage you to watch. But I download these notebook and also Wang and IBM color quantum computers. So we can maybe go back to look at the code. Okay, so I think I have this one. Yeah, we saved this, but let me make sure I have the code run. So it's a simple circuit, and this define the observable. This is simple, so there's no optimization done here. Here meaning classical optimization. Optimizing maybe the circuit or yeah. So here we just use estimator. In this case, the estimator is also V1. Qiskit error primitive. This is estimator. This is V1. Okay. To get the V1 value, you just say values, result of value. Okay. So to the post processing, like last time I said that let's convert to V2, right? I hope you also did while I was doing that. So use state vector estimator. So we could really check if really V2. But this is the estimator. It's implementing this base estimator. So Qiskit primitive base estimator. You could also let me search this. State vector estimator. So I think yeah, you use estimator V2. State vector estimator, simple implementation of the base estimator V2 with full state vector simulation. GitHub. You could, if you really want, you can also go to GitHub and to see this state vector estimator. So remember in the early beginning we talk about class and the children. So this one state vector estimator, it inherit this base estimator V2. Right, so you can use, so there will be base estimator V2 and use some of the function there. Okay, this is just the documentation, initializations, property. And so if you're really a Python person, you want to really know how they design, you go to this. the reason I mentioned this is because remember we talk about quantum algorithm. We use quantum algorithm, Qiskit quantum algorithm, and this was maintained by the community, and it actually is still V1. If one could change that, then we could have more flexibility and run it on devices. Because the V1, you cannot use that to run cases. Qiskit algorithm. Oh no, this is oh this is from the ecosystem, meaning that if you see the ecosystem, this is not necessarily the IBM, but the IBM with the community. They call it ecosystem. I don't know they would how soon they will revise this to V2. They also have primitive. Maybe the latest update. Okay. There's no okay. This latest update is the IBM in quantum in general. Yeah. If you look at the VQE, okay, I'm just you see the estimator, okay, estimator. Estimator. So its type is base estimator. So the IBM um, algorithms is using the type 1. So well, V1. Yeah, because when I was preparing the material, I was thinking maybe I should uh, write and then change that to V2. So, but I don't think I can do it by myself. There's also a gradient. Okay, we digress too much. But for us to go to V2 is simple. Here, we just use state vector if we're not worried about running on the device. So we already have the circuit, we already have the observable, and we can just put in the pub. Right, so this is the observable result. Right, you can see that there's a shape 6 because we have 6 observable. Probably we don't need. We just have dot. That makes sense. Okay. So, and in extracting the result, you use EVS. This is for the V2 data, EVS. V1, let's compare that. It's really just, it's values, right? So it use values. Result of values. Okay. Then I said we could also use runtime. And then use this V2. Can we use bar? Yeah, we can use bar. Tell me how to use that. Is you need to change something. Bar. Yeah, let's see. I hope this is this. We need to have well We need to have the six separated. Oh, maybe this is what's ZZO. I think it's doing something. Maybe I don't need this perhaps because okay. Oh, that may be too small. The value may be too small. How do I let it? I mean, this is really just matplotlib thing. Okay, let's see. Since this is a programming, we we can spend some time learning these. I hope they have example. The easiest one to have example. The easiest one to have example and just try it. Okay. Yeah. This one. Bar level. Bar label and let's see. Color. We don't understand about color. This is the X. This is Y. Label. Color. Okay. Oh, should say bar level. X. Is it X? That set Y. Is it going to shut off the? It seems it's going to shut off the light
Okay.
because we moved.
Yes.
Uh, it should also be the same, right? Set X plot bar value. Oh, label bar level. Okay, so it's not for that. Okay, that's just it. Okay, maybe that should be set by level.
Hi, Professor.
Yeah,
The
set
set
by
X
level.
label and the set Y label functions are for the access object specified by AX. If you're using PLT, like in our code, just go for X label and Y label instead of set X label and set Y label.
You mean I just put in the bar here?
The
Oh,
set
I
y
should,
label.
yeah.
No, the PLT dot set y label should be PLT dot y label, just that, not set y label.
Oh. But the value does not show up because it's too small.
I believe it has to be an integral value to at least show up on the plot. This being a bar plot. This is strange.
The values is too small. Oh, why is it? It automatically. Oh, it's. Oh, I see exactly 0. Yes, because we're using the state vector. We're using state vector, so it's exactly 0. That's why we don't see any value. Okay. You could do also for the following one. We're using simulator. We use air simulator. Okay, we run. So we're using V2. So we use circuit observable. So let's do this. And we're removing this. That's what is the value. Still, go back here. This one has somehow the value is negative. Okay, I mean, that's not, we have too much on this. Estimate results. It's not, what did I change? Check the results. Check the results. Oh, it's using V1, so I'm using the V2 language to extract this. Okay. Right. Okay, so this is indeed showing the negative values here. Okay. So this is the hello world. And I think this is the last time we were here. So he defined a function to create n-qubit GSC state. You start with initializing the quantum circuit. You do the Hadamard for the zeroth qubit, and then you do the subsequent control knot on the remaining one. Okay, so this is the large qubit number. We might have seen code similar to this when we were comparing the air simulator and the simulator. Okay, let's do just do the 20 qubit circuit. So this is really simple circuit. Okay. And this is to show the observable. So observable is really Z. So you can string how many I's separated the Z's and the rest. this. Okay, so this is the ZIZ. So as Z goes further and further away, it's really measuring the correlation, how it decay, how it behave as a function of the distance. Okay, so here there is some optimization. Yeah, so here, so use the task manager to optimize the circuit. So here, the first is to choose the least busy backend. So you say it's not a simulator and it's operational. Minimum number of qubit is 100. And we use the path manager according to this backend optimization level 1. You transfile. And once you transfile, you get the circuit layout. You need to apply that layout to the operator. So operator.apply layout. Okay, so to get this, we are waiting for which is the best, least busy backend. Oh, okay, it's still waiting. And once we have that, we'll print operator transpile. So you see it's mapped to which image. All right, so now we have it. Right, so the operator used to be just, we have 20 qubit, right? But once you map to the real device, it's actually have 127 for this one. We can do this from Qiskit visualization. I think we can plot circuit layout. Is there a circuit layout? Circuit gain, something like that. Let's see if an error that's import. Yeah, indeed there is circuit layout. So let's plot circuit layout for this circuit. Transfile circuit. QC transfile. What's missing backend? Yes. Okay. So you can see which 20 qubit was selected. It was selected here. So this is the 0, 1, 2, 3, 4, 5, 6 to 19. So from 0 to 19, it's selecting this. Because we are using the CNA, right? So it's when it's optimizing the circuit, it knows that it need to choose a line graph. Okay, so you play with this and then execute on backend. Okay, I'm not going to run this. So to run this, as we saw in the yeah, as we saw in the slide. So this is how you do it. So there's an estimator options if you want. So this resilience level, right? You could also use two There's also other things called dynamical decoupling. This is error suppression method, and it can specify what kind of sequence. So XY4. If you don't know that, you can always do the search. It's like XK, YK. It's so there are dynamical decoupling. There are a few options. Yeah, there's only XX, XP, XM, XY4. So this is the more detail. XX uses tau over 2. This is the sequence plus X tau plus X tau over 2. I think what they mean here, tau over 2, maybe you're not doing anything, but that's the time. And you apply XK and then wait for this, and then XP, XM. So this is plus X is minus X. Even though plus X and minus X in our circuit doesn't matter, but in the real house they differ by a minus. XY4, this was the one chosen. Tau over 2 plus tau plus X and tau, and then Y minus X minus Y. So you inserted tau over 2 at the end, and in between you have tau spacing. Okay, so maybe I'm going to copy this. For dynamical decoupling. Okay, so you can search, but next edition I'll have this. Okay, but we can maybe just copy the options. I think sometimes when you search something, it's useful to just write down the results, so you don't need to go there every time. Just going to this. Okay. So then I think every line we understand what's doing. Estimator, again. Options. I think here you could use mode equal to backend. So if you don't write that keyword, then it would just according to what it would take this as the mode and then options. If we run this, and okay, so I'm retrieving the The service results. What machine was it used? Just to be curious. So I think it was from Strasbourg, but let me not erase that. But the current one that we have chosen, it's a different machine. So every time depends on how busy. So, but this code was from Strasbourg. Okay. So let me retrieve the job. Even if you lost this, you can always go back to the website and see what's the job ID. Okay, this is plotting this data from 1 to the operator length. So, and then this is result, and this is the data, right? So values, V for V in values. And then you plot this together. This is the distance. This is the operator normalized by this first one. Okay. Oh, I didn't, did I? What's this? Here. X and Y must be the same side. I must have changed. Oh, I must have changed the right. So I was using 20, right? So I don't know what's the number that I chose. This is this data equal to this. Because he's using the operator. So I should probably data equal to this. No, this is a okay. So then we will know. Just say data equal to list of range equal to then let's not use operator. Use the value. Oh, this is using 100 qubit. GG state. Okay. Here you might, yeah. I think you could also use a plot and then draw the line. Okay. Just to say make sure. Okay. This is the real device. Okay. Yeah. You have some question? The other one is for the primitive, and then next will be dynamics. Let's see. Have I uploaded the next one? last time this notebook was uploaded. Okay, I think I uploaded. Yeah, all the notebook. Lit 064. Wait. Yeah, I think I upload. Yeah, there might be one last one, but okay, we can look at the second one. But I hope by now you sort of know this. Yeah, know the how to use this. In the beginning, we've been using the simulator that run, and now we sort of make transition to sampler estimator. So primitive, okay. This is the second one we're going to see from Darren Ron's notebook. This may be related to the lab. One of the lab is actually using this Ising model. Okay. Okay, so this should actually just put something like this. Okay, I don't know where it is, but we can, yeah, we can always put a link. There's also the video. Uh, showing you the video. Again, it's going to, somebody should move. Yeah, as long as you, yeah. Yeah, so this is the list of all the video, but this notebook is the longest one. So I'm not going to play, but it's like
So first, what is a primitive?
Okay.
In computing, a primitive is the smallest processing instruction for a given abstraction level.
Okay. But I think by now you know what primitive is. Okay, so what it's doing here? So first we import the quantum circuit, Y gate, unitary gate. So we know these gate, right? From very early that we look at the standard gate library, import numpy x Y gate. Okay, this is the square root of Y gate because it take power one half. And then this is the dagger. This is the inverse. Okay. You generate one-dimensional transfer field Ising model. So number of qubit, total step, x angle, number of classical bits, total variable, layer variable. If there's no classical bit, then you don't put in an argument. If there's specified number of classical bit, you put it. Total step. So this add 1D transverse-field Ising model, total layer. So this is defined, this function is defined here. On circuit.
So here one layer is like all even.
I would think it's probably two, like even and odd, right? 1D. So of all these number of qubits, it's doing the 0, 1, and 2, 3, 4, 5, right? So you have a one-dimensional qubit. You do the 0, 1, 2, 3, 4, 5, etc. Yeah.
Why do we want to mirror that?
Let me see. We do the S gate, SDG. We append SY gate. We do the C naught. We append this SY layers. Okay, these just will add. So this is adding RZZ in the even there, but I think it decompose by itself already here. So this is RZZ. There's a Ising model. There's a ZZ interaction, so it's doing that. This is for the even there. So I don't want to. You can perhaps verify yourself. Okay. You first apply the S dagger on the I plus 1, apply the square root of SY gate on the I plus 1, apply C naught, and apply the inverse of I plus 1, or I plus 1, give it. Yeah. Perhaps this could be an exercise. RZZ. Yeah, it does not have. And this will be doing the same thing for just the labeling is different. This is doing so this is doing RZZ for 80. That's chosen some time duration. Exponential minus I CZ. But X here has an angle. So the duration is different. So this is for the This is for the. It should. I think it should here. Say, if I want to be complete, maybe I said add x rotation. So basically, it's really just e to the I. I don't know where that would show that. That's a minute. Minus I x, maybe it's over 2, rotation of x over 2, x angle. Right. So there's a define these 6 qubit. Try to step this one. The angle is showing the circuit. So yeah, this is the, they call it odd or even. Okay, call it even layer. Here, even layer. This is doing the RZZ, and then odd layer, X rotations. Okay. You don't need to know what the Ising model is, but it's like ZZ plus X. But it's turning that into a circuit. Okay, what exactly do they want to see? Sampler, so you will see the distribution. Okay, so this, let's see what are the functions. Mirrored 1D transfer Ising model circuit. And okay. Okay, he put some notes. Constructed inverse by hand here. Could also use this done inverse is doing the inverse of the circuit, right? So put the negative value of the angle and do RZZ in R layer. Basically, just reverse the angle and then RZZ. You also need to do the dagger.
So
here.
it's
Yeah, so it's doing forward and backward. Right. Yeah, so this is the same. So it's just right. X. Okay, so this is the inverse. Okay, drawing the inverse, a mirror, append. So this is appending the mirror circuit to that. So then what you can do is to measure if it go back to 0. Yeah, the problem is right, absolutely. Okay, 10 step.
So it's just for benchmarking.
Yeah, you can see. Yeah. So it evolve 1 step and go back. Evolve 2 step, go back. Evolve 3 and see how it.
So it's like checking how it how
Yeah, how the
error
machine.
accumulates.
Yeah.
So
If you cannot go back, then you have error accumulated. Okay. But because see, it put barrier, right? Charter barrier and layer barrier. So it will not, when you do the translation, then it will not do the combination across the layers. Okay, so okay, we're getting the back end. Then you run on the hardware. You see that they are also using the XY4 here, just like the above. So yeah, I'm not going to run. But it will take a while, and So we retrieve the job. But one thing we should take a look is here. This is a list of circuit, QC list. QC list is how many product step. Okay, so I'm going to retrieve the job. Okay, and also this is a V1. They're using the V1. Wait, sorry, they're using V2. Here they use V2. Right, so they use V2. To run that V2, I think usually you need to use pub. And pub will be a list of these pub, and it has circuit, observable, or here is sampler. So only circuit. If you have parameter, there's no parameter here. And also number of shots. But I guess, but if you only put circuit, well, for what he has shown here, you could just use the list of circuit. Okay, so we're going to retrieve the job. And retrieve the job. Remember, we have 10 jobs, so you use the trotter step to retrieve the job, and the data survival probability would be the one that has 0 counts. Right? All of them are 0, and divide the number of shots. Okay. If there is no such data, I mean, if you don't get 0, all 0 bit string, you append the probability to be 0. Was there a question? And let's see. Okay, these were alt. Okay, so we're going to plot that. Okay, this was the result, but let me just plot it again. Oh, there's a different. This is probably the one that I ran, and maybe the previous one was from the notebook. Okay, on the notebook here. From his
Goes up again.
yeah. So and that's probably not something that is really real. Okay, this is the circuit. I just want to see his results. Map. Okay, observable. So you can watch the video. Where is the results? This is probably the first. You see. Oh, so here there are some observable. So this is probably the one that we want to compare is early. Simpler. Okay, I may not be able to get the screen that he showed the result. Okay, let's not do that. But this is the result that I read. Because if this is his result, I cannot retrieve his job. So it must be fine. Okay, so yeah, it does not look as smooth as the previous time that it has. Goes up and down, up. Okay. And here just adding observable. And also the parameters. So here we have a parameter of x rotation, right? So previously here, this x, here we specify already angle. But we can use parameters. So this is basically combining a lot of things we have learned. Now this is parameter, x angle is parameter. And you generate 1D transfer field circuit. So this is only generating that forward, there's no backward. Okay. Right. So remember here, we generate 1D transfer field circuit, and then we do also append the mirror, we let it come back. So here we only do the forward, and then what are the observable we want to measure? So for example, this is the middle index, so and you want to do the observable, only measure one location, the z operator at that location, to see how it is evolved. Okay, so this also, we need to optimize this circuit. We use the here we just use simple transpile. Okay. Yeah. So in his recorded video, there's a transpile, but it says the transpile will be deprecated. So the future use generate preset path manager. This was not down here. So yeah, one really trivial homework is use a path manager to do that, and then try different optimization. You can try different optimization level and see the results. Okay, so this is that. Oh, so plot circuit layout. You see. Oh, I thought was it not here? This is for the hello world. It did hello. So let's see for this. Oh, this is slightly different. Wait, which backend? Okay, this is a different backend. It has more qubits, so it's flooding in a different way. So it's very interesting that the way It's like 100 qubit, right? This is 100 qubit result circuit. It's like doing this. It goes around. Yeah, in the past we also did 102 qubit experiment. You have to find the path. We basically did it. We find a path on our own. It's not periodic. Periodic, you will have to link this.
Oh, the end of the chain there.
So it's interesting to see this, right? To just good visualizations. That's why it's useful to take the existing code and then play with it. Okay. This is V2. And then it will try different angles. There are 12 different angles, and you you create this list of these angles. Resilience level 1, we've seen it's using some minimum mitigation, right? Dynamical decoupling, XY4. It seems Dr. Wang like XY4 a lot. The two notebook here use XY4. But I've seen other use XX. Okay, estimated V2. So now he put the QC transpile circuit, observable, X angle, this, yeah. So this is, we only have one observable. So it will be 1 times number observable, the output. Okay, I'm not going to run this. And this is the output. Okay, I'm retrieving from the job. X angle list is not defined. Okay. You saw the diagram. So let me not run. I need to have the angle defined. Okay. Yeah. So this is the angle. 0, it looks very good, right? 0 angle, it's still, it's 1. And then start to like decay, oscillate.
This is the expected behavior.
It does not, no, this is the experimental result. The expected, I don't know. Yeah. One can easily simulate. Maybe you can simulate. You can simulate with the MPS.
Yeah.
Try do that. Okay. Yeah, so this is also at the end. Let me comment this.
Sometimes it's like the TV.
But it's doing the, if you want to simulate this circuit, you're doing the discrete. Yeah, you're doing the discrete. Yes. Yeah. Yeah, in MPS you can also use discrete types. Yeah.
Yes.
Matrix they have the simulations. Oh, what one could do is, remember we have the simulation MPS. One could simulate. Maybe that's a good. Let me just put it here. I would say a good exercise is to use IBM's MPS simulator to predict the observable center. Okay. To use their own, I think there's a simulator you can do that. So this will be useful.
But is it like normal MPS?
They're using MPS, but how they implement. I don't know.
Oh.
But it might also be available if you look through the code. Okay, so this is probably a good time to stop. And next time we'll go to the other notebook that he has, and you can watch the video if you want. Then also is the documentation I want to go through. Classical feedforward. Because it will use a dynamic circuit, you go for measurement and then depending on the outcome. Okay. Any question?